who will be telling us about moving towards broadband nulling and fringe tracking with 3D photometric tricouplers in GLINT.
Yeah.
So please take it away.
Good morning, everyone. So I'm postdoc at the KU Leuven, but what I will introduce you for the next 15 minutes in my work done at the University of Sydney with the first integrated optics nuller made and deployed at the SCEXO. So with nulling, and you heard it but before, the whole week, it's about exoplanets and again exoplanets. And we want to hunt them, to characterize them with nulling, which is the interferometric equivalent of coronagraphy, but unlike coronagraphy, we'll be able to probe much closer to the neighborhood of a star and to probe ideally the habitable zone. If you see, for instance, this picture of HR 8799, but we have this wonderful picture from coronagraphy, but if we want to go to the habitable zone, which is the green circle here, you need a better inner working angle that can be provided by the nuller. So another how it works, you just have two apertures or two telescopes, you combine them so that one of the beam is pi shifted with respect to the other one, so that you have two outputs, a constructive output when you have your starlight, and another destructive output when you have either no light or the light of an off-axis source like a planet. So GLINT is the first integrated photonic nuller. So its core element is the integrated photonics. All the assets, advantages of this technology has been presented by Aline before. Here in our case, the instrument is set on the Subaru telescope behind the SCEXO system, and we are more like an aperture masking nuller instead of a long baseline nuller. So we get the light from the telescope, 4 subpupils to get 4 apertures we want to combine together. And we inject the 4 beams into the photonic chip, which will be in charge of remapping the 4 two-dimensional configuration of the remapper into a linear array, which is more convenient than to do a pairwise combination of the light. The instrument operates in H-band and provides 6 interferometric baselines. For each interferometric baseline, you have 1 constructive output where you get the starlight and 1 destructive output or a null output. All of these outputs are then spectrally dispersed, and we get the spectra of all of them on of a detector. And while we are pioneering nulling, we try to pioneer as well a new way of data processing. One is based on called the numerical self-calibration, because we want to get rid of the time to observe a calibrator and dedicate it to 100% to the starlight. So what we plan to do is to model, to understand the statistical behavior of your data set in order to infer the astrophysical observable you are interested in. So for the last 3 years, the instrument has been commissioned in lab and on sky on lab to really know, of course, how the instrument behaves. And for instance, here on the left, you have the coupling ratio inside the directional coupler that we use in GLINT to combine the light. And we can see that there is a kind of chromatic, which is perfectly expected given the technology, but we'll see later the consequences. And on sky, we wanted to measure a stellar diameter of Arcturus here. So with 4 baselines, we managed to recover the diameter of the star. So that means we know how to do nulling and how to process the data with the NSC. The main interesting thing with GLINT for the last 3 years is more like what is the next steps to go in deeper null into improve the efficiency of the instrument. And with GLINT, we found 2 improvements possible, 2 limits to overcome. First, the directional coupler, which delivers a chromatic null depth. GLINT has air delay lines, which are also chromatic. So it's a bit of a shame when you have a spectral dispersion and you want the best null possible and you are just screwed by some chromatic effect. The second thing is that despite GLINT being on SCEXO, which is an extremely adaptive optics, you still face huge phase variation, like for instance, low wind effect and so on. So this huge phase variation cannot be properly modeled into the NSC currently. And what we had to do was just to sorting the frame and throw away 50% of the frame so that we can still keep into a hypothesis of a small, normally distributed phase. So there's these two main axes of improvement we want to do for the next development of GLINT. And for that, there is a useful photonic component, which is called the tricoupler. So the tricoupler, this time, you couple the light into 3 waveguides and you recover it from 3 outputs. The geometry of the tricoupler is the main interest here, which is the 3 waveguides are disposed according to an equilateral triangle. And thanks to this geometry, when you have 2 wavefronts in perfectly 180 degrees phase shifted, you have an achromatic null depth, because by this geometry, you cannot couple the combined light, the interference, into one of the waveguides. So if you have an off-axis source perfectly in phase opposite, you have no light in one in your waveguide, regardless of wavelength, perfect extinction over your wall bandwidth. It's what we are looking at. The second advantage is that with your 2 others outputs, you have something which is an ABC cell, so like an ABCD combiner. So you are coding and you can recover the phase, which is extremely useful, either to know the distribution to put into the NSE, or even better, use it, feed a fringe tracker servo loop, and stabilize the signal. So that's all the promise we want to fulfill with the tricoupler. And here there is some plots. The bottom left, you can see that when you are 180 degrees for fringe tracking, you can see that if you go left or right, the 2 lateral outputs with changing phase in different directions. So you can know how much the phase you deviate and in which direction. And on the bottom right, what you can see is that when you have a perfectly phase opposite of a wavefront, you have a solid flat answer for all your outputs, and some chromatic effect if you are no longer in phase opposition. So that's a lot of simulation work so far on the tricoupler, but the first batch of the real tricoupler by the Macquarie University are coming, and we are quite happy to see that we start converging toward what we aim to. So between the left, which are the simulation, and the right, the result, we want them to converge, which is just a matter of finding the good parameters of the ultra-fast laser inscription and design of the properties of the device. To exploit and to really go to a complete achromatic, GLINT use RDLA lines. And it's a shame that this RDLA line, which are chromatic, and we have an achromatic device, so it's a shame to halve the performance of the tricoupler because of another component of instrument. So we want to plug in front of each tricoupler some achromatic phase shifters. So no secret here. We just do, like, I think, Gravity or Pioneer, where we change the section of the waveguides in order to have this almost achromatic phase shift at less than a degree. And if we plug it in front of our tricoupler, we're happy to see that now you have wavefront in phase, we are shifted by the APS, and you have a flat response of null and of the lateral output. All this work has been done by intern Teresa Clino-Theo, and she's preparing a paper with all this work. So we have this tricoupler which allows us to tackle the achromaticity and the phase distribution. But how behave a planet light? Because you want to conserve a starlight, but you will also want to have the best throughput of a planet light. So we are trying to fiddle to optimize the design of a tricoupler to maximize this planet light throughput. For instance, you can see here, and it's very empirical, but when you change the distance between the waveguides on your triangle, you change as well the spectral response of an off-axis source conveniently located half a fringe away from the source, from the star. And if we increase by just a bit the pitch between the waveguides, we manage to have a more even spectrum, instrumental spectrum of the planet light. It comes with an expense. We are decreasing the fringe tracking capability. And we discover that either you get a tricoupler who can be good at doing fringe tracking, but not that good at planet light throughput, or vice versa, a very good planet light throughput, but a limited fringe tracking capability. So this is my takeaway. GLINT is an extraordinary demonstrator that when you combine integrated optics, multiple baseline spectral dispersion, adaptive optics, it's really the way to develop nulling for exoplanets science. We commissioned it on sky by measuring stellar diameters far below the diffraction limit of instrument. We identify the two main limitations a nuller should tackle if they really want to reach deep null, which is the chromaticity and the phase diversity. So to tackle that, we use a tricoupler and achromatic APS and some simulation, assuming a perfect world, show that we can hope to win a factor 45 on the raw null depth, and with the NSC, you can refine by a factor 10 or 100, so that GLINT would be, and we really hope so, to reach the contrast of 10 to -5, which is the minimal requirement to see a planet light. So the next step, that's creating all that stuff, optimizing the filling of the pupil, see Peter Stetil talk and poster in SPIE, integrated all these new things on GLINT, and we also want to enhance the data processing with machine learning techniques, and I redirect you to Barnaby's Norris talk on SPIE in July. Thank you.
Okay, thank you very much. Questions? Okay.
Yeah, Gail Schaefer from the Char Array. So I just was wondering, during the on-sky commissioning, have you attempted to detect faint companions? And if so, what level of contrast have you achieved so far?
Sorry, I didn't understand the question.
Oh, so you've done some on-sky commissioning?
Yes.
Okay, and have you looked to see how faint companions you have?
Not yet. The only companion we have is a binary system. We want to process the data. The main difficulties here are more like to know the orientation of a GLINT pupil, which is quite hard to characterize on SketchSound directly, and the NSC method, which is not completely on point. Because we need a huge amount of data before getting something, like 20 minutes of data at 1400 Hertz. So when you want to observe the modulation of the null depth, we have a lower, so we need to think about how to increase the signal-to-noise ratio of the method and complete the characterization of GLINT and with SketchSound, within the SketchSound.
Any other questions? No? If not, I had a quick one. So you're talking about the tricouplers. Are the benefits compared to sort of gravity style coupling, okay, are you expecting to be able to push to longer wavelength ranges, or is it just that you get better achromaticity in the same kind of wavelength range?
So, so for the same range for GLINT, we expect a better achromaticity. And then, yes, of course, I said geometrical consideration should work for every wavelength, but then I guess you have all this propagation into the different piece of glass and absorption. So it would be hard with the same piece of glass to get a very achromatic thing from H to the edge of K.
Yeah. Yeah, I think that's something we'd all like, though. But yeah, that's completely understandable. Okay, no more questions. We can thank our speaker again.